Hello everybody, my name is Gadi Taubenfeld and I'm going to speak about a joint work with Michel Raynal. And the title of the paper is Fully Anonymous Consensus and Set Agreement Algorithms. So let me start by explaining what is full anonymous systems are. So first let's start with the notion of anonymous shared memory. Anonymous shared memory is as follows. If we look at the classical view of shared memory, we have the processes, and the processes communicate via shared objects. So if one process, say the yellow one, wants to write something and tell something to the red process, then the yellow one writes it in some memory location, say X, and later on the red can come and read from X. But this requires that they a priori agree on the name of this memory location, that when they go to X, they go to the same memory location, okay? And the notion of anonymous shared memory means that we don't have this a priori agreement. In some sense, the memory location do not have names. What happens is that each process names the memory location as it wishes. So the red one names it in some way, so it calls this memory location 1 and this memory location 9, and the blue one gives another set of names, so it calls this one A and this one G and so on, and the purple give another set of names and the red another set of names and so on. So there is no a priori agreement on the names of the memory location. Each process gives its own set of names, uses its own set of names. So I first introduced this memory model, this weak memory model in this paper at POTSI 2017, and since then there were several follow-up papers, interesting, that cover both algorithms, impossibility results, and lower bounds for various problems in those papers that you can see here. And what we do in this paper, we take a one step further, and we're going to assume that also the processes, not just the memory, also the processes are anonymous. Okay, so anonymous processes simply means that the processes do not have names. So full anonymity is when both the processes and the memory locations are anonymous. And this is what we're going to investigate in this paper, full anonymous systems. Some motivation for studying this very weak model. So first, theoretically, it increases our knowledge of what can be done in the context of full anonymity. So it's intellectual curiosity, basic research. So this is a theoretical motivation. The more practical motivation is that from application-oriented point of view, we know by now that you can use full anonymous systems to model biological systems. Okay, so full anonymity can be used to model biological systems, and I can refer you to this, I think, interesting, very recent paper in which we model a biological system, define a problem using the full anonymous memory and full anonymous memory and processes. So full anonymous systems, define a problem and solve it in this model. So you're welcome to read this paper. Okay, so in this work we cover two problems, set agreement and consensus. So let me define those problems. The set agreement problem, we have the processes here. Each process has an input and should output some value. And the definition of the problem is that each output should be the input of at least one process. And we're going to require that at least two processes output the same value. Another way to say it is that if we had n processes and we look at the set of all outputs, then this size of the set is strictly smaller than n. So we have at most n minus 1 different output values. This is set agreement. Consensus is it's a stronger version in which we require that all the processes agree on the same value, output the same value, okay? And as before, the values that they output must be the input of at least one of the processes. Okay, so what we're going to do next, we're going to solve the set agreement problem. We're going to start with that for n processes, where n is any number that you want. So you can say, okay, let's solve n processes, take n to be 1 million, and the solutions that I'm going to show you is going to work. But first, I need to define what obstruction freedom is. So obstruction freedom simply means that the progress condition that we require is that each process decides as long as it allowed to take enough steps alone. So if a process runs alone without interruption for a long time, for a long enough time, that is, it takes enough steps, then eventually it decides. And this is the only progress condition. This is the only correctness condition that we require. It's weaker than what we call wait freedom and other progress conditions. So it's a very weak progress condition, but it is known that consensus can be solved in this assuming obstruction freedom if consensus and set agreement can be solved if we assume only obstruction freedom if the memory and the processes are not anonymous. And we're asking, can it be solved when both the processes and the memory are anonymous? So here is a solution for set agreement for any number of processes. Okay, so we're going to use 3 registers, and they are anonymous. And by registers, I mean atomic registers. So the register are going to support atomic read-write operation only. So you can either read from a register atomically or write atomically to a register, but you cannot do something more complicated like reading, computing something, and writing it in one atomic step. So the first step that a process does, it first read all the 3 memory locations in some order. So they're going to read the memory location in different order possibly. Then it checks what is the majority value, that if we see some value that appears 2 or more times in this over here, right? Then it's going to, so again, if the process C, after doing this, that some value appears 2 or more times, then it's going to write this value into its local variable, which is called my preference, and this is going to be the value that the process supports. I should say that initially all those locations are considered to be empty or having some special value, say bottom. And bottom is not a value that they decide upon. So when they check, when they read and look for values that appear 2 or more times, this does not include the initial value here, the bottom, because just think that the locations are empty. So reading an empty location doesn't return a value. Okay, so once you have set your preference, and of course, if you don't see that a value appears 2 or more times, then you have your initial preference here, which is set initially. My preference is set to your initial preference. Okay, so now you know what your preference is, and you try to find a register among those 3 registers such that its value is different from my preference. And if you find such a value, then you write your preference into that registers, and you repeat. And what you try to do is you stop when you find out that all the 3 local registers equals to my preference. Okay, so you go over here, you read the 3 registers, and only if you find out that all of them has the same value, you go out of this loop and decide on the values that you saw in all those 3 registers. And this would solve set agreement for any number of processes. I will let you convince yourself that this is indeed the case, and you have proof in the paper. Okay, so this is the set of steps that we do, and so on. Okay, so here is one observation. It looks trivial, but we should say it. This algorithm would work even if instead of using 3 registers, we use any number of registers bigger than 3. So for example, it would work also if you have 5 registers. Now, this is not trivial with anonymous shared memory, because with anonymous shared memory, it might be the case that you have an algorithm that you can solve with, say, 10 registers, but the algorithm and the problem is not solvable with 11 registers. So the fact that you can solve a problem with some number of registers doesn't imply that you can solve it also with more registers. You know, without anonymous shared memory, you can simply say, if you give me more registers, I can ignore them. So obviously, if you give me more registers, and if I can solve it with 10 registers, and obviously I can solve it with any number of registers bigger than 10. But not in this model, because if you want to ignore some register, you have to agree on which register to ignore, and this is a hard problem. Okay, because in this model, we don't have a priori agreement on the names of the registers. Okay, so we have this observation. And another observation that the same algorithm, you know, and this is usually the case, if you can solve set agreement for any number of processes, and the same algorithm would work and solve consensus, the stronger problem, consensus, for 2 processes. So if you restrict yourself only to 2 processes, then the set agreement problem said that those 2 processes have to decide on the same value, so it's solving consensus for 2 processes. So here we know how to solve consensus for 2 processes. Now the question is, how do you solve consensus for more than 2 processes, say for 3, for 4, for 5, for any number of processes, using only read-write registers? Okay? So the first idea is to say the following. Let's assume that we have, instead of 3 registers, let's use 2n-1 registers. Okay, and we update the algorithm. Okay, so this is an adaptation of the algorithm. So we replace the 3 here with 2n-1 registers. We have some same number of local registers that we can read the shared memory into those local registers. And we do the same algorithm, but now, initially, we just read the 2n-1 register into local memory. And if some value appears in more than half of them, then we write this value to my preference, and we try to, you know, as before, we try to find out registers with a value which is different from my preference. And we continue until we see that all the registers are the same, and then we know that, that we can stop. So the question is, does this algorithm solve consensus for n processes? And the main thing to see here is that if we look at this reading the memory, then if we think about reading the memory in 1 atomic step, so if we can read the whole memory, the 2n-1 registers in 1 atomic step, we call it a snapshot, then this algorithm would solve consensus for n processes, where n can be any number of that you decide a priori on. And why this is the case? If I read all the 2n-1 registers in 1 atomic step, and I see that all of them are the same, so I can go out of the loop and I decide on some value, then I can be sure that any process that will come later will decide on the same value, because the other processes, we have n-1 other processes left. Each one of them can initially, before it reads all the registers, it can destroy one of those registers, write something different than what I saw in at most n-1 memory locations. But the majority value will not change. So each process, once it does this line of this code, will switch to the values that I decided on. and we eventually decide on the same value. So this algorithm solves consensus for n processes, assuming that we have a snapshot available and we can read the whole memory in one atomic step, all the registers. Now, would this be correct if we assume that you don't have atomic snapshot? That is, we read those registers one after the other. And surprisingly, the answer is no. If you simply use read-write registers without atomic snapshot, then in the paper we have a counterexample that shows that this algorithm doesn't solve consensus even for n equals 3, even for 3 processes. For 2, it will solve consensus. For 3 processes, it will not solve consensus. And the proof of that is rather complicated. So you have it in the paper. Okay? So this leaves us with a question, and this is an interesting open question. Is there a fully anonymous consensus algorithm for 3 processes or more using only read-write registers? So think about it. That's, I think, an interesting problem which we thought, both Michel and I thought about for some time, and so far we couldn't solve it. So maybe next year in NETYS, you would have a solution and you would have a paper. Thank you very much. And if you want to ask me a question, here is my contact information. Just send me email. I would be happy to get some feedback from you. Thank you very much.